solutions, I believe. So we talked about, again, that basically it's made up of two parts, the solute, which is the smaller part, plus the solvent, which is the larger part. And we talked about a couple of other things involving solutions, including we talked about electrolytes. And remember, electrolytes are guys that will break apart into ions. And will conduct electricity. And there are strong that break apart. So you pretty much have all ions in solution. Conducts electricity really well. Have weak electrolytes, which actually mainly stay together. But you do produce a few ions, so it's still able to conduct electricity, but not as well. So can conduct electricity, but not as well as a strong electrolyte. And then we had also weak electrolytes you can really recognize by the arrows that head in both directions there. Strong electrolytes typically have a one-way arrow, which will basically stay together when they dissolve. No ions are produced. And a result of that actually is they will not conduct electricity. We finished up, I think, talking about equivalence, which is sort of a way that we can look at ions in solution. And the number of equivalents per mole is related to the charge. So if you had something like sulfate, the charge there is 2. It has really nothing to do with it being minus or positive. We could say for every 1 mole of sulfate, we get. If we had something like sodium ion, charge there is 1. We could say for every 1. Did a little calculation at the end there with an ionic compound, where the basis of an ionic compound, right, is to make sure that we balance out all the positive and negative charges together. And what we saw there was, in terms of the concentration of the ions that are floating in solution, the concentration of the positively charged ions and the concentration of negatively charged ions, they end up being basically the same in terms of equivalents per liter and stuff like that. So that's one way you can kind of look at the charge sort of concentration in a solution is equivalents, or a lot of times equivalents per liter are milli equivalents per liter is oftentimes sometimes how that's used. So sometimes you also see MEQ, and that is milli equivalents. And it's the same sort of milli conversion as you do like milliliters to liters. So there'd be like 1,000 milli equivalents in 1 equivalent. So it's kind of very similar, obviously, to that conversion. Any questions on any of that there? Okay. So I think we left off with an example here. So let's take a look at that one there. If an intravenous or IV bag, which often given in equivalents per liter or milli equivalents per liter in terms of their concentrations of sodium chloride, contains 154 milli equivalents per liter sodium ions, how many milli equivalents of sodium ions is a patient given in 800 milliliters of the solution? So why don't you take a second, see what you come up with. Okay, let's take a look at this one. So really, this is just a conversion here. We are given 154 milli equivalents per liter. and we're going to give the person 800 milliliters. So we do have some unit issues here. One's in liters. Obviously, one is in milliliters. So we need to convert the milliliters, perhaps the liters. We divide it by 1,000. Or move the decimal place, whichever way you prefer there. Gives us 0.8 liters. We would then take that, times it by the 154 milliequivalents per liter of our sodium ion. The liters would cancel each other out. And we would end up with here, 54, about 123 milliequivalents of sodium ions was given to the person there. Question on that calculation there. So once again, this is a very common, especially for IVs and stuff like that, it's very common kind of concentration for a solution of ions, basically. Any questions on that one there? Okay. So let's talk a little bit about solubility. Solubility is the amount of a solute that will dissolve in a given amount of solvent. A lot of times we report sort of how much we could get to dissolve as how many grams per 100 milliliters of solution. Now, if we have a saturated solution, that basically contains the maximum number of grams that you can of solute that you can get to dissolve in a solvent at a particular temperature. So if your solution is saturated, you pretty much have hit the point where the maximum amount of that solid will dissolve. If you continue to put solid in there at that point, it will not dissolve. So it'll just kind of pile up there at the bottom at that point. Solubility is sort of temperature dependent. So at a particular temperature, you could get a certain amount to dissolve. If you change the temperature, increase the temperature, a lot of times with solids, you could get more to dissolve, but it is sort of temperature based. The opposite of that, or I guess before that happens, you have a unsaturated solution. And an unsaturated solution is a solution where you pretty much have not hit that point yet. So in an unsaturated solution, if you take the solute and you put it in your solvent, it will continue to dissolve. And it will continue to dissolve until you hit a saturated solution, or sometimes referred to as the saturation point, basically. So an unsaturated solution, you haven't hit the maximum that will dissolve there. You can continue to get more to dissolve and more to dissolve until you really hit a saturated solution at that point. There's also one that is referred to as supersaturated. A supersaturated solution is one where you have really too much solute dissolved in a solvent. And it creates, for the most part, a fairly unstable solution. And typically the way that you make a supersaturated solution is you basically make a saturated solution. As you're making that saturated solution, you heat it up. By heating it up, it's going to do a couple of things. It's going to allow you actually to get more solid to dissolve as the temperature increases. It's also going to essentially evaporate off some of the water component there of the solvent as well. And what you'll end up with after you sort of heat it up, get a lot more solid to dissolve, is you'll sort of end up with a supersaturated solution. And typically you let it cool back down, usually in this case. And as it cools back down, a couple of things happen. The solubility changes because now the temperature has come back down. But at this point, you've already gotten all that solid to dissolve in there. So you have this solid that's dissolved in there, or the solute that's dissolved in the solution. And it realizes at some point when it comes back down in terms of temperature, It really shouldn't have that much in there. And it creates a solution that is super unstable to a point where if you just took like the speck there, a little thing right there on top there, whatever you dissolved in it, and you drop just that one little speck in there, what will happen is that will be enough to kind of send this guy over the edge and go, no, too much in here. And what will happen is this solution will go from a solution and all the solid will basically just come right out of solution, and it'll go from a solution really to sort of a rock hard solid, as all the solute that was dissolved in there at the higher temperature now has nowhere to go basically, so it comes out of solution. It is so unstable. I've done experiments at schools where I just go to like lift the little test tube or flask, and then just a little shaking of the lifting part is enough to make all the solid come out with actually not even having to put a crystal in there. So it usually is a very unstable sort of solution. Because of that, you essentially get way too much of that solute sort of dissolved in there. Any questions on any of those things there? So why does things sort of dissolve in each other, or why are things sort of soluble in each other? As we talked about when we're talking about those intermolecular forces, those are really the things that determine, will something sort of interact well with each other. And it brings up the idea of like dissolves like. So things with similar intermolecular forces will typically be soluble in each other. So what does that mean? It means for the most part, if you want something to be soluble, if you take something that's ionic and polar, that's all going to be good. They're going to be able to use ion and dipole interaction. Again, kind of how pretty much sodium chloride, for example, dissolves. You got something that is polar and polar, they are definitely going to be able to interact well with each other. And if you have something that is nonpolar and nonpolar, they will also interact well with each other. Polar and polar things could use dipole-dipole interactions. They can use hydrogen bonding if that's possible for them. Non-polar guys will both be using dispersion forces, so they're able to interact well with each other. You really kind of only run into a little bit of a problem here when you try to cross over there and you take something that is polar and non-polar together. Again, they typically will be insoluble in one another because they have, as we talked about, really kind of no long way of interacting with one another. They both could kind of use dispersion forces for a little bit, but that's not going to basically be able to maintain that interaction. So they will eventually sort of separate out from one another. So if we take some sodium chloride, as I mentioned, and some water, that's going to give us like our ion dipole interaction. As we talked about with intermolecular forces, basically those ions are going to be surrounded by the positive and negative side of water. And that's essentially what helps something like sodium chloride dissolve. Even though to us it looks like it's totally gone, it just went away. It really didn't go away. It just got surrounded by a ton of water molecules, each of those ions. So visually we can't really see it anymore. It kind of works its way into the water network. So once again, your positive ion would be surrounded by the oxygen part of water, which is more negative, and the negative ion would be surrounded by the hydrogen part of water, which is more positive. And again, that's what basically allows something to dissolve in water. Small neutral molecules are soluble in water, especially when you have something like oxygen or nitrogen that has the ability to hydrogen bond. So this is ethanol here, and ethanol again really looks something like this. If we draw it out real quick here, yeah, it looks a little bit like that. And really, ethanol is a organic molecule where it pretty much has, I think I might drew methanol the other day. It has non-polar part, but it still has this OH bond here, which is very polar. And that is a hydrogen that is bonded to an oxygen, which is essentially what you need for hydrogen bonding to occur. Remember, for hydrogen bonding to occur, you need a hydrogen directly bonded to an oxygen, nitrogen, or fluorine, which is those really electronegative atoms that you have. And because it has that OH group, it allows it to also participate here with water where it's negative and positive. And obviously here you could get some hydrogen bonding to occur. So that's going to make something like ethanol actually soluble in water because of the presence of that OH group. Solubility really does start to decrease as this nonpolar part gets larger. So usually around 5 or 6 or more carbons there, solubility drops way down. Yes, sir. Between what two things you say? This one? Are you asking, is this bond polar? It is slightly polar between the carbon and the oxygen, but if your question is, can these guys participate in hydrogen bonding? They cannot because they're not attached to a nitrogen, oxygen, or fluorine. So it's really only this sort of hydrogen that can basically participate in hydrogen bonding because it is attached to the oxygen. It's slightly polar there between the carbon and the oxygen because the oxygen and carbon are slightly different guys, but the majority of the action will happen there at the OH group. Now, if you build out that nonpolar part with a lot of carbons, and again, all these would be hydrogens all the way across here and on the bottom. And you just have this one little OH group over here. Like I said, it's what is sometimes referred to as steric hindrance. Got this big giant nonpolar part that really gets in the way of that interaction. So it makes it really hard for water to kind of get in there and interact really well with it. And remember, essentially, if something has to be soluble in water, what you essentially have to do is replace basically the water-water interaction, right? So you got to break those water-water bonds before you put anything in there and replace it with something very similar. So again, at some point, these molecules get way too big to really fit nicely with all the waters, and they can't really, sort of interact well with each other, even if they still have that OH bond there. So usually about, like I said, less than 5 carbons on there, and it has got that OH group, it's good to go, but solubility drops a lot as you go through there. Nonpolar compounds, again, are soluble in nonpolar compounds. Sometimes people miss that one thinking, well, it's nonpolar, but they are really soluble in other nonpolar guys because they both are using, again, the same type of interaction, which is those dispersion forces that we talked about, which is really the weakest of all those interactions. But they will be very soluble in each other. So, if you took something like octane and you put it in carbon tetrachloride versus octane in water, and the carbon tetrachloride, it is going to look just like that one layer. If you took the same, say, octane and you threw it in water, you are not going to see that. You're going to definitely see some layering that's going to happen between the two, where up on top there would probably be your octane, up on the bottom there, or down on the bottom would be your water layer, and they will definitely separate out from each other. Again, because the water down here going to try to use hydrogen bonding. He's using dispersion forces. In this case, everything will mix good because everybody is using those dispersion forces on the bottom. So they interact the exact same way as they basically interact with themselves. And that is essentially the key to solubility, is if you could find somebody else that will interact pretty much how you interact with yourself through those intermolecular forces, they should be pretty much soluble in each other. Any questions on that? Now, when solvation releases energy or more energy than is required to separate the particles, it is an exothermic process. And the separation of these particles, the process is endothermic if less energy is required. And, sometimes these processes overall in terms of energy is an exothermic one, which means, again, that heat is released or heat is absorbed if it's an endothermic process. So how do we know if we sort of take a couple things and sort of put them together. Would we expect them to be soluble or insoluble in something like water? We could use really this what's on the table here, which is a solubility rules. And these are solubility rules which help us understand what things are going to be soluble or not. So when you put together an ionic compound in a reaction, how do you know what you get on their side is going to be soluble or insoluble? So first off, if we use solubility rules and it's determined to be soluble based on solubility rules, typically these are the guys that will get that aqueous symbol next to them in a formula. And if based on solubility rules, they are determined to be insoluble, these are the guys that will get the solid sort of symbol next to each other. So let's take a look at some of these rules. Rule 1, a compound is soluble if it contains the following. Anybody from group 1 on the periodic table. So as soon as you see in a chemical formula for an ionic compound that it's got somebody from group 1, is going to be soluble no matter what the situation is, no matter what it is hooked up with. It is always going to be soluble and aqueous. And also, if you have anything that contains ammonium, which is NH4 plus, it will also be soluble. There are no exceptions to this, which means it will be 100% pretty much soluble all the time. Rule number 2, a compound will be soluble if it contains the following. If it contains chloride, bromide, or iodide, it will be soluble, but there are some exceptions. And some of the exceptions are if any of those guys, the chloride, the bromide, or the iodine, are hooked up with one of these 3 guys here, which is the silver 1 ion, that is the mercury 1 ion, the next guy, the guy with all the 2s, and that is lead 2. So it would be the opposite. So normally chloride, bromide, and iodine are soluble. And if it happens to be one of these 3 guys involved, then it becomes insoluble and you would expect a solid to form. Nitrates are soluble in everything. There are no exceptions. So if you see a chemical formula that has NO3 in it, it is always going to be a solution. It's always going to be soluble, which is why probably in the laboratory you use a lot of solutions to say something nitrate. And that's because they are soluble pretty much in everything. So it's a very easy way to get things into solution by mixing it with nitrate. Acetate, which is the next one of those polyatomic ions, are also pretty much soluble in everything. So there are no exceptions. So once again, if you see acetate in a compound, it will always be soluble. Sulfate, which that should not be a 2, that should be a 4. There we go. So SO2 4 minus is soluble in everything except when it hooks up with barium, mercury 1, or lead. So those guys would then be insoluble. So these guys would be a solid. These guys here will also be a solid. And everything else on this side would be the aqueous symbols here. Any questions on that there? We have more. So let's see how we could kind of use this. Let's say we had a reaction, like a double displacement reaction, where we took some silver nitrate, and you probably have done this reaction somewhere, plus some sodium chloride. It's going to do a double displacement reaction, going to make some silver chloride and some sodium nitrate. So let's say we wrote this reaction. We want to know, hey, are these guys going to be aqueous? Or are they going to be solid? We could use our solubility rules here to help us along. So first off, if we come here, although we may not see silver, I do see nitrate. And when I come down here to nitrate, it is soluble in everything. So there's no exceptions. So as soon as I see that, I know that this guy should get the aqueous symbol, and it's basically going to be a solution. I see sodium, which is basically rule number 1 up here. That is group 1. And that really is as far as I need to go to determine that this guy also should be soluble and get the aqueous symbol. I could also look at the second one if I wanted to in this case. That is chloride, which is soluble in everything except for silver, mercury, or lead, which is not the case here. So it is also going to tell me that it is soluble. When I come over here, I see silver, but yet I see chloride, which we just talked about, which is soluble in everything except for silver. So because that is chloride that is hooked up with silver, is going to be the opposite. It is actually going to be insoluble. So when you do this, you'll make a white solid, and that is the white solid that you make, which is the silver chloride. And the last one here, sodium, again, is pretty much as far as I need to go because that is soluble in everything. So that would be aqueous and soluble. Once again, we could also look at the nitrate, which is soluble in everything as well. So you could use your solubility rules here to determine whether or not something will be aqueous or solid. All right, so as I mentioned before, you should be familiar with the solubility rules. They probably will be provided for you, but you do need to know how to obviously use them. Solubility, effective temperature, and pressure. As I mentioned, most solubility is based on temperature, and typically you can increase the temperature, will increase the solubility of a solid in a solvent. And really, because as you increase the temperature, you're adding more energy. And as you add more energy, that's going to allow everybody to kind of come apart and start separating and allow the dissolving process really to occur. So they sometimes say, you know, if you are trying to dissolve something and it really won't dissolve something, you could kind of slowly heat it up a little bit and it will start to probably dissolve and allow that solute to go in there. As I mentioned earlier, supersaturated solution is once again one where you sort of do that process of sort of heating it up. It allows more of it to dissolve. And again, it creates that unstable sort of solution. The solubility of gases decreases with increasing temperature, and that is because gases are normally soluble in each other because they're frankly just flying around. So just by that process, they are mixing. But if we increase the temperature of a gas, we would expect that gas molecule to fly around a lot faster, which means they really won't be by each other for as long, and they really aren't mixing very much in that case. Any questions on that there? Yes, sir. Yeah. Yeah, so typically if you wanted to make, for example, a supersaturated solution, you would start by pretty much dissolving like a solid in a solvent, and you get as much as you could get in there. But the goal there is to really get way more than you should have. So typically when you do that, you're also heating up that solution at the same time. And what that's going to allow you to do is basically get more of that solid to actually dissolve. So because you're heating it up, it's going to actually increase the solubility of that solid. So that's going to allow more of it to really dissolve. And typically the second process, usually when you make a supersaturated solution, is after you get as much dissolved as you want, you kind of kill the heat and you actually just leave it kind of sit there because you don't want to touch it too much because it becomes really unstable. And it will start to cool back down. So as it starts to cool back down, what happens is really the solubility now starts to go back down and decrease. But at that point, you've already gotten all of it kind of dissolved. And that's why it creates sort of this really kind of unstable solution because at that point, it's still dissolved, it's still a solution, you know, if you leave it kind of cool back down, not really touch it. But it's a very unstable solution where if you just really knock it, it's enough for it to realize, oh, that's way too much. This shouldn't be dissolved. So basically all the solid comes out of solution at that point. Yeah. Other questions? Okay. So the effective temperature and pressure is also sometimes referred to as Henry's law. And this is the idea of our soda can, for example. Under high pressure, for example, before you pop the soda, in the liquid part, you have a lot of CO2 basically dissolved in it. So under a very high pressure, you have a very small volume. So the gas comes down in terms of volume and it sits in the liquid part of your soda. Then we do two things, right? We pop the top, right? And once we pop the top there, you will see sometimes the fizzing coming out, right? And that fizzing is the CO2 that's basically escaping. And you basically did two things there. You obviously released the pressure, so the pressure went down, which means the gas volume is going to go up. So it's going to find itself outside of the liquid part of your soda. You also, by popping the top there, gave it actually the CO2 an escape route, right? That it could actually fully escape your soda. And that is why, right, when you come back later, your soda tastes very flat, right? If it's been sitting open for a while. And that's because basically all the CO2 has now less dissolved in the liquid part, and it had an escape route basically to leave your can completely. And now again, you're just left with a sad flat soda that you drink and go, oh, should not have done that probably. Yeah. Any questions on that there? So there's actually a calculation you could do with Henry's law to calculate the solubility and the pressure, but we won't cover that here. So now let's talk a little bit about some important concentration units. So some of these are the percent concentration units. So first one here is percent weight to volume. Most people also call this mass to volume, percent, and sometimes abbreviated percent M/V for mass to volume. And that is the mass of the solute divided by the volume of the solution times 100%. And basically, you know, if we had, say, a 5.25% mass to volume sodium chloride solution, what that would mean is we essentially could take this percentage and just assume 100. We would have 5.25 grams of sodium chloride in 100 milliliters of solution. So you could kind of use it as a conversion factor if you're given the percentage and just assume 100. You could obviously use it like that. You could also flip it around the other way if you needed to. Also, you clearly can just plug and chug into this equation here to figure out the percentage as well. So why don't we try that there for an example? Vinegar contains 5 grams of acetic acid in 100 milliliters of solution. What is the weight to volume or mass to volume percent? So looking at this one here, this is basically percent mass to volume. And that is our mass of our solutes divided by the volume of solution. And we do want to times it by 100. So put in our numbers would give us 5 grams divided by 100 milliliters, kind of like the density, right? So this is basically 5 divided by 100 times it by 100 gives us 5%. And that is sort of how people will leave the answer. If you want, you can leave it as 5% mass to volume, whatever this is, acetic acid. Okay, so questions on that one there. So another sort of common unit, percent unit, is volume to volume. This is sort of the unit we use for like alcohol, for example, percent by volume. And that is the volume of the solute divided by the volume of the solution times 100. And again, this is also sometimes abbreviated like that, percent volume to volume, or volume to volume percent. And in this case, if we were to look at this, if a bottle of rubbing alcohol contains 70 milliliters of 2-propanol and 100 milliliters of solution, then the volume to volume percent would be, so our volume percent would be our solute volume, which is the smaller, which would be the 70 milliliters, and our larger part, which would be the 100 milliliters times 100%. And in this case here, we'd basically take 70 divided by 100 and times it by 100, going to give us 70%. Rubbing alcohol, basically, volume to volume. Question on that one there. Now, a more common sort of percent concentration in addition to these two here is what is sometimes referred to as mass to mass percent. And that also is a very common sort of one. So let's take a look at that, I think. Actually, let's do it here. So another one is percent mass to mass. That's M/M. And that is the mass of the solute divided by the mass of the solution times 100%. Now, unlike the other two that we just saw, in most cases and problems, the volume of the solution is just given to you as the volume of the solution. In these type of problems here that involves mass to mass percent, oftentimes the solution is broken up in the problem where the percent mass to mass would be the mass of the solute. And you want to make sure that you actually get both, the mass of the solute plus the mass of the solvent times 100%. So very common in these type of problems, they're sort of separated. So for example, if we made a solution by dissolving 55 grams of sodium chloride and 125 grams of water, what is the mass to mass percent? So why don't you take a second and see what you come up with. Okay, if we look at this, we have 55 grams of sodium chloride dissolved in 125 grams of water. This is our solute. And the water here, which is the larger part, would be our solvent in this case. So our percent mass to mass is the mass of the solute, which is 55, divided by the mass of the solution, which we do want to take to 55 and actually add it to the 125 grams. And that is going to give us the mass of the solution. Again, it's a very common thing that people will just take the solvent value there and divide by it. So you want to make sure that you do add both of those together. And if you do that there, that's a 55 divided by a 55 plus a 125 and times it by 100. This is approximately 31% by mass sodium chloride here. Any questions on that one? So that's a very common unit of solutions, and it is again very common that the solute and the solvent is separated from one another. Any questions on that one? Yes, sir. I got 30.5, and in this case, I went with the top number was 55, which is 2. The bottom number, when we add that, I think we get like a 180. Yeah. So basically, it's 2 divided by basically 2, if you want, or 2 divided by 3. So it should end up probably around 2-ish. But yeah, I got 30.5555 on the calculator. Yep. Other questions? All right. So I'm going to go back to this one that we skipped. A saline solution used in an IV is 0.92% mass to volume sodium chloride. How many grams of sodium chloride is contained in 250 milliliters of this solution? Okay, so let's take a look at this. So here we're looking at percent mass to volume. Again, same as weight to volume. And we can actually sometimes just use this as sort of a conversion factor. Sometimes maybe easier and just sort of do it as like a conversion problem. So when it says 0.92% mass to volume, what that basically means is we have 0.92 grams of sodium chloride in 100 milliliters of solution. Or again, you could use it as a conversion factor the other way, 100 milliliters up on top and 0.92 grams of sodium chloride. So you can kind of take a dimensional analysis approach. And in this case, we are looking for how much is in 250 milliliters of solution. So 250 milliliters of solution, we would want to use the conversion factors such as this one here. And that would get us 0.92 grams of sodium chloride in 100 milliliters of solution. Milliliters of solution will cancel each other out. And we will end up with here 2.3, it looks like, perhaps, grams of sodium chloride. If I punch in the right numbers, let me just double check. Divided by 100. Yep. So there's 2.3 grams of sodium chloride in this case. The other approach is you could just go into the formula, obviously, and just put the values in, which mathematically is the same thing that we just did here. The mass of the solute, volume of solution times 100%. In this case, we obviously had this number and this number. So you can multiply the volume of solution to the other side, which is that, and times it by the percentage and divide the 100, which is this. So it's mathematically the exact same thing. If you just want to plug and chug, obviously, into the formula there. Any questions on percent concentrations? Yeah. So we just assume 100 because it keeps the numbers the same. You can assume any number you want on the bottom, but then the top number would change. So it's like whenever you have a percentage, we'd like to just assume 100 because it just keeps the percentage number basically the same. So if you had 5%, that would be like 5 grams of 100 in 100. You could assume 200, but then it would be like 10 grams in 200. So you got to adjust the top number too. So it's sometimes easier just to assume 100. This is where that comes from. Yes, sir. Say again. Yeah, if you change you mean the 100 part there? If you use some other number, I would just advise you just to use 100. It just keeps it simple. It's the same number up top. If you did change the bottom, you got to adjust the top number accordingly. So it depends what number you choose for the bottom. But if you choose 100, then it keeps the top number exactly the same as the percentage, which in most cases is much, much quicker for you to use that way. Yeah. Like if you said you got 90% on your exam, that usually meant you got 90 out of 100, right? So it's just easier to just convert it into a usable sort of number or percentage if you assume 100. Other questions on that? Okay. All right. Now, sometimes solutions are very, very small in terms of their concentration. So sometimes they are given to you in parts per million. Parts per million are parts per billion is what the other one probably should say. And basically, you're just taking the mass over the mass and times it by that factor there. Probably parts per billion, I'm assuming on that one. PPB. We're not going to do too much with that, so you don't have to worry too much about those guys. But what we're going to talk about now is really the big unit of concentration, the most commonly used unit of concentration, which is molarity. So pretty much most solutions, molarity is really the concentration unit that you use. Molarity is abbreviated with a big M, and it is moles per liter. It's technically moles of solute per liter of solution, which is basically what it says down here. And you could think of this as a formula, and it's very common that we solve for any one of these three things. So if you wanted the liters, which is a very common thing, you would take the moles and divide it by the molarity. And if you want moles, which is a very, very common move, it would be liters times molarity. So those are a couple of rearrangings of those equations, which you use a lot here. Do you have a question? You're good. Now, I highly recommend get rid of the big M when you're using it in a calculation. So if you had something that was 4.5 molar, which is how you refer to that big M, sodium chloride, that is basically the same thing as saying you have 4.5 moles of sodium chloride per liter of solution. So the number always stays with the moles part, and it's always 1 liter in terms of molarity. The reason I say when you do calculations, you should do it probably more like a dimensional analysis problem and get rid of the big M is because when people leave the big M, in the calculation is very common. They have clearly no idea where like the volume is. They forget about it a lot of times. They're not sure, am I dividing by the volume, multiplying by the volume? So when you convert that big M into these two units here, you could clearly see both of the units. And, you know, if you take a more dimensional analysis approach to it, it will allow you to, you know if you should be multiplying or dividing. Now, a couple of things sometimes, and a lot of times we need to go from grams to moles to calculate the molarity. And to do that, once again, it is the molar mass that we want to use from the periodic table. So that's a common thing that you need to do in calculating molarity. This right here, which is a very common use of molarity in moles, the volume does need to be in liters. So it's a very common thing that people leave it in like milliliters and multiply it by the molarity. And the answer is, can you do that? Yes, but you do not get moles. You actually get what are known as millimoles, which is different by a factor of 1,000 and stuff like that. So if you're ever sort of standalone using molarity and volume, you want to always make sure you convert it to liters and then multiply it by the molarity so that everything cancels out correctly. Or if you're calculating, obviously, the molarity, you want to make sure that that volume does get into liters. The higher the molarity number, the more concentrated it is, the more strong of a solution. So if you see on a bottle it says 18 molar hydrochloric acid, you should be super careful with that. Yes, that'll like melt your hand right off. Yeah. You got 16 molar nitric acid. You know, if you ever come across those things in lab or something like that, you should always open those acids very, very slowly and dispense them very slowly. And you probably should be inside a fume hood at the time when you're doing that. Otherwise, it will give off a lot of very strong vapors. If you think about a lot of solutions maybe that you use is like 0.1 molar, maybe 3 molar, 6 molar, you know, it's a lot less, you know, in terms of the concentrated. So obviously the smaller the molarity number, the less concentrated it is. And that usually means more diluted. And what that basically means when we do a dilution is we basically just add more solvent or water, which basically increases the bottom number here and brings the molarity down when we do that. All right, so why don't we try one here? Calculate the molarity of a solution that is made by taking 20 grams of sodium hydroxide and putting it in enough water to make 250 milliliters of solution. Some numbers that might be helpful for you from the periodic table. Sodium is 2299. Oxygen is 16. And hydrogen is 1.008. Okay, let's take a look. So obviously we are calculating the molarity, which is moles per liter. If we look in the problem, we actually have the liters part given to us. We do need to convert it though, obviously, since it's in milliliters. That means we're really missing the moles part here, and we could get that by using the grams that was given to us. So in this case, we do need to get the molar mass of sodium hydroxide. So that is basically adding everything we got going on right here, right? So we're going to add all those guys together, and that's going to give us basically 40 grams per mole, since we have one of everything there. So the first thing we'll do is convert our grams into moles. So just like normal here, we'll use the molar mass of the sodium hydroxide, grams on the bottom, so it cancels. That's going to give us 20 divided by 40, gives us 0.5 moles of sodium hydroxide. We do need to convert our volume into liters, so you can move the decimal place, or once again, divide by 1,000. Gives us 0.250 liters, divided here by 0.25 liters, really. And that gives us moles per liter, divided by 0.25, gives us 2.0. And you can leave the units since they don't cancel as moles per liter of sodium hydroxide. So that is one way you could write it. You could also write it just 2.0 big M sodium hydroxide. So you could leave it like that as well. Either one is fine. Any questions on that? In terms of sig figs, my 250 milliliters was 2 significant figures. So basically at the end there, 3 divided by 2 gives us 2 sig figs on the end. Yeah. Any questions on that one there? So again, a very common mistake people make is not doing that liters conversion. So you want to make sure that you definitely do that. We can use, as I said, molarity as sort of a conversion factor to calculate volume, to calculate, as I rearranged it there a second ago, moles per liter, liters, moles divided by molarity, and a most common one, moles, liters times molarity. So those are, again, sort of rearrangements of those. So why don't we try one here and see? Okay, let's take a look. So if you're not sure, obviously we're dealing with molarity, which is moles per liter. In this case, they gave us the molarity and they gave us the moles. So obviously here we want to rearrange it and solve for liters, which would be moles divided by molarity. Once again here, personally, I will kind of convert this into a sort of conversion factor. And again, that means that is 0.30 moles per liter of glucose. Or again, you could use it in the opposite direction, liters up on top, 0.3 moles of glucose there on the bottom. So in this case, we have 0.025 moles of glucose. And once again, we could just think of it like a dimensional analysis problem where this guy would go this way. We would end up with liters up on top and 0.3 moles of glucose on the bottom. We're essentially dividing by the molarity, which is essentially what we were supposed to be doing. Once again, the moles of the glucose will cancel, and that would get us 0.025 times 1. Don't need to do that. Divided by 0.3 gives us 0.083. The units here are liters. In this case, though, we are looking for milliliters, so we want to multiply that really by 1,000 there to take us from liters to milliliters. And if we do that, looks like 83 milliliters of glucose in this case. So once again, you can put it into here, but sometimes it's just easier not to lose the units and kind of do more of a dimensional analysis sort of approach to it. Yes, sir. Yeah, you should round. So you want to follow sort of the normal sig fig rules. So basically, we're pretty much only doing like multiplying and dividing in this situation. So really, our first number here had 2 sig figs, right? So basically, we had 2 sig figs here as well. So really, this guy should end up at 2 sig figs. I think you kept going with 3s on your calculator, right? And then this last one's an exact number, so you wouldn't look at the conversion there. So you would probably want to maintain those 2 sig figs at the end. Yeah. Other questions? Question on molarity here. Very, very common unit of concentration. So let's just talk also this way. How's that? Let's go this way. Let's talk a little bit about molarity and ions and sort of how that works. So let's just say we had a 0.25 molar solution of sodium sulfate. And let's say we were interested in a solution, what is the concentration or the molarity of the sodium ion and the sulfate ion in solution that may flow around. Since this is an ionic compound, when that guy goes into solution for a swim, it is not going to stay together. It will break apart into sodium ions and sulfate ions floating around. So sometimes you're asked about the concentration, the molarity, maybe not of the whole thing. especially with ionic compounds, but maybe a specific ion or both. So the way that molarity works is like this. If you took the sodium sulfate in solution, when it breaks apart, you will get 2 sodium ions and a sulfate ion, right? And if the concentration of this guy is 0.25 molar, you could kind of do like a stoichiometry relationship to figure out what the concentration of the sodium ion would be in that solution. And if we did that, it is basically a 1-to-2 relationship. So you get twice as much sodium ions for every one of those guys that go for a swim. How that affects concentration is you would actually take the concentration and multiply it by 2, which means the concentration of the sodium ions in there is 0.5 molar. Now, when we look at the sulfate, it is a 1-to-1 relationship, which means basically you would multiply the concentration by 1, which basically would give you the exact same number. And the concentration of the sulfate ions in molarity would be 0.25 molar. Obviously, you can see molarity is different than equivalents per liter because it is not additive. They don't add up to the same number. But what it tells you is basically what we kind of know. There's twice the amount of sodium floating around. So the concentration of sodium ions there is twice as much. So if it breaks apart into a 1-to-1 relationship between the whole ionic compound and the ion, the concentration will be the same for the ion. Breaks apart into like a 1-to-2, you multiply the concentration by 2, 1-to-3 multiplied by 3, and so forth. That is really the short version of the longer calculation. And just to show you what the longer calculation looks like, this is 0.25 moles of the entire thing per liter. Doing stoichiometry from the equation, 1 mole of the whole thing gives us 2 moles of the sodium ion. Whole thing cancels. Basically, we're multiplying by 2 there, and we end up with 0.5 moles of sodium per liter, which is the molarity of the sodium ion. And if we did it for our sulfate that way, it is a 1 mole of sulfate to 1 mole of the entire thing. Those guys cancel, and we end up with 0.25 moles of sulfate per liter. Hence the multiply by 2, multiply by 1, basically, is the quicker way of doing that calculation. But that's really the sort of long way, right way, I guess, of doing that calculation. Question on that there. So why don't you try one here? What would be the concentration of, let's see here. If we had a 0.15 molar potassium phosphate solution, what is the concentration of the potassium ion and the phosphate ion? Let's see what you come up with. So this potassium phosphate will break apart into 3 potassium ions and 1 phosphate. And since the whole thing here is 0.15 molar, it is a 1-to-3 relationship for the phosphate, which means we would take 3 times 0.15 molar, would give us 0.45 molar for the phosphate ions that are floating around there. And since it is a 1-to-1 relationship between the whole thing and phosphate, it would be 1 times 0.15 molar. Gives us 0.15 molar would be the concentration of the phosphate. Any question on that one there? All right, we will stop there for today.